I don't think they're all going to be as exciting as this one.
Wow.
It'll be exciting if you sing.
Yeah, try, go for it.
I will. Oh, so no, supper. Mega fun time.
Oh, you're right. It is supper.
Wow. You're welcome.
Supper. We'll leave it at supper. We'll leave it at supper.
Supper.
Who doesn't like supper? I love supper. It's like I've made it through the whole day and I get this beautiful time to sit down and eat it. Supper, mega fun time, human feedback experience review. So today, does anyone have questions for me before I launch into the review? Like for the review. Did anybody come prepared to ask me any questions? No? Yeah?
I had notes. I think I'll have questions as we start. I say, maybe you'll come back. Yeah, like I know I have questions, but
yeah, some of this will be easy. Some of it will probably give you flashback support. No matter. That depends on how far I get through this, but I was thinking Tuesday because I'd like to put the water behind us so we can move on.
Nice. Okay.
All right.
Our trigonometry test is
Yeah. How do you guys feel about that that color scheme?
Looks pretty cool.
I know, very, very much so. Okay. I start with this guy. What?
You want me to sing the whole thing?
I don't know. It's up to you. Do you want?
Is the pervading law of all things organic and inorganic, of all things physical and metaphysical, of all things human and all things superhuman, of all true manifestations of the head, of the heart, of the soul, that the life is recognizable in its expression, that form ever follows function. This is the law. The tall office building, artistically considered 1896.
Yeah, that's it. This is already on Google Classroom under the PowerPoints entitled, I don't think it's called Supper Mega Fun Time Human Review.
Test 1.
Test 1 review. There it is. Yeah, that's what the slide was like before I left my apartment. So, what was the point here? Can anyone drag the point out of the deep recesses of the early semester? September. Throw your minds. Form follows function. Okay. What's another word for form?
Shape.
Shape. Okay. What was the word I used? Yeah. What? Okay. What was so? Mars eloquently recapitulated Lewis Sullivan's pronouncement here that the function that something has is going to dictate the form that it takes. Form ever follows. And I say, excellent. And then I took this idea and I wanted to extend it. And I said, what word did I use what was the other word that I used? Form? And you said shape. Structure, that was it. Yeah.
Building.
Whoa, what's going on? Yeah, structure. Yeah, the structure function paradigm. I talked about the structure function paradigm, and this is the idea that the shape of something, the structure that it has, is dictated by the function that it needs to. All right, do I need to write that on the board? Okay. The structure of something is dictated by the function it needs to serve. Form follows function. Right? And this is the guy that first said it, but he tried to make it the sort of a universal relationship between these two concepts. The function something serves and the form that they you should remember his name insofar as when I say when Lewis Sullivan was talking about, or Lewis Sullivan was talking about the structure, whatever, how would you articulate it? For example, I'm not going to ask you to drag it out of itself, but you recognize. Yeah.
We're talking about his.
Yeah, what do you want to say?
Moses parting.
It looks like someone started to haircut like straight down the middle, and then
Yep.
figured out he was on the cops.
Reverse mohawk.
Yeah.
Well, okay, well, listen. Form follows function. So the form of his hair follows that he will never have sex in his life.
Oh, you know, he was quite a dapper dude in his day.
Actually, yeah.
In his day, Lewis Sullivan was quite a celebrity. Yeah, he was quite a celebrity. Enough of that. Okay, so this gets extended to anatomy and physiology, right? Why did I even talk about this? It's because these are reflected in anatomy and physiology. Anatomy, structure. It can be the microscopic structure. It can be the structure of a protein. It can be the structure of a biomolecule, but it can be the structure of an organelle, cell, or a tissue, or organ, or an organ system. The anatomy of something is its structure and is dictated by the function that structure needs to serve, which is the concept of physiology. So what I was doing by introducing structure and function was trying to give you an understanding of the relationship between anatomy and physiology. Does that make sense? Is that incorporated? These are. I'm not putting things on this slideshow that I'm not going to ask you. So, the hierarchy of complexity. I then introduced this idea, which should be an intuitive concept, that smaller things make up bigger things, and that there are these sort of distinct levels of organization that we can consider, from atoms to molecules, macromolecules or biomolecules, into organelles, cells, tissue, which then makes up organs, and there are components of organ systems, and then, of course, that makes up the whole organism. All right? So those are the levels of complexity. This idea that there are organizational levels that an organism is made up of. And so each level has constituent parts from the level below it. Everyone good with that idea? Yes, sir. Oh, yeah, thumbs up. All right. There are some chemical concepts I want you to understand. And the chemical concepts are that there are atoms in the universe that are connected with bonds. There means these atoms are held together to form molecules. And there are two different ways they're held together. They're covalent bonds. It's where they share electrons. And ionic bonds. And ionic bonds is donation of electrons. All right? No. It means that I have this nice and I could loan it, donate it. But, and so now you're happy with that codon. You, major, probably are more concerned about whether you look cool in a cool coat. I don't care so but it is my coat. I'm loaning it to you, and you go out and do your thing. But I think to myself, oh, she's got my coat. I'm going to stay close to her because she has my coat. Or better yet, even let's do it like this. Imagine two people who, and we'll take the same coat paradigm. We'll put it right in your real life. Has anybody ever given their jacket or sweater or something like that to someone that they liked, that they were sweet on, their significant other? Yeah, okay, understands that. And you do that, and thus by donating that thing, you are drawn to that. So that's what this is like here. There's this electrostatic interaction between them. Once one atom donates its electron, it becomes positively charged, more positive. This one becomes negative, and those opposite charges are attracted to one another. So once the donation happens, it doesn't mean like, see you later, you have my coat, remember me. It's here's my coat. I like you. I'm sticking. Right?
Okay.
That kind of. All right, molecules. So what was the point here? The point was I wanted to show how water is formed, basically water, which by these covalent bonds, the sharing of electrons, the formation of covalent bonds. There's not actually a whole lot in this slide. I probably didn't include it. But this one, it was like prepping us for this idea that water itself, because it's not, that electrons don't share, atoms don't share electrons evenly. They don't share electrons evenly. And so this would be like, I'm gonna make fun of it. I love vinyl records, and like for birthdays or like that, I will get my children or my wife records because that's what I know, and I try to get them records that they like, and so they enter those records into the family, and they're a shared resource, a shared thing, but they're not really shared equally because, frankly, the rest of them don't care about records as much as I do. And so even though it was a gift I gave to them, I am the one that's usually putting it on the record player and playing the record. All right, so it's like an asymmetrically utilized shared resource. And that's what happens here. It makes oxygen, oxygen's kind of greedy about the electrons and makes it a little bit negative. The protons are a little positive. Not completely so, but enough so that we have this, what's called a dipole moment, like a little magnet form. And it's that property of water that gives water a lot of, it's the underlying chemistry or physics behind a huge amount of your physiology, a lot of the things that drives the physiology in your body. It's the polarity of the water molecule. There's like a negative pole and a positive. It's like there's a northern pole and a south pole. There's some polarity to it.
So for this slide,
that water is a polar molecule.
Negative.
Positive. That's correct. And that one of the things that enables is water to dissolve ionic compounds. So those the like letter jacket scenario that water is able to kind of get in there and surround the ions and actually take them apart and allow them to go what is called in solution. All right, ionic molecules are able to be in solution because of the polarity of the water molecule. All right, so this water is a polar molecule. This allows ionic compounds to dissolve in water. salt. That has sodium chloride right there. So sodium is a very important cation, and chloride is a very important anion. Those two together make up table salt. Another important feature of water is its ability to form hydrogen bonds, which leads to its surface tension, leads to all kinds of things like the fact that ice floats, which is sort of weird, and that there's this thing called capillary action. So here's some water, green water, and it's wicking its way up this little glass capillary action. Capillary action is important for how blood flows. It's not magic because of these hydrogen bonds. Other kind of forms, transient bond formation. You can imagine this, instead of being like going steady with someone, it's more like being. And like those change, you know. That I run with, you know, it's like that. It's these different friend networks that shift and evolve. The concept of an acid and a base. I feel like I expended quite a bit of personal capital on this one, goodwill and capital, so I would be remiss in completely abandoning it. An acid is a molecule that acts as a proton, aka hydrogen ion donor. It's something that will give up a hydrogen, whereas a base is something that will accept it. And water can break up into a hydrogen ion and what's called the hydroxide ion, but this is a base because it is a proton acceptor. Right? Acids and bases. Proton donor, proton acceptor. That was to set up the concept of pH. So the pH is a measure of acidity. It's really just the concentration of the hydrogen ion in solution. So the higher the concentration of hydrogen ion, the more acidic. But because the concentration is so low, we take the negative log of that concentration. So this right here, 10 to the negative 7th, is this is the concentration of the hydrogen ion in water. And 10 to the negative 7th, that number in particular, is distilled water. That's like pure, natural distilled water. If there are more protons, so this is 1 out of every 10 to the negative 7th. So 1 10 to the negative 7th of the molecules is a hydrogen ion. If that number is 1 times 10 to the negative 4th, that's a larger number, right? It's a larger number than this. Do you guys believe me? Is 10 to the negative 7th bigger or 10 to the negative 4th bigger? Which number is bigger? Yeah, okay, right. This is a bigger number. This number means there's more hydrogen ion concentration. But if you take the negative log of that, following all this, the negative log of 10 to the negative 4th equals 4. The negative log of 10 to the negative 7th equals 7. So, and we call this negative log, we call that pH. pH, the negative log of the proton concentration. As pH goes down, as the pH number goes down, it's just referring to the fact that the hydrogen ion concentration is going up. So as pH goes down, it's more acidic. As pH goes up, it's more basic or alkaline, more of a more base, right? You guys follow that idea? Okay. I think that's all of that. Then onto this, I started talking about the elements of life, what human beings are made up of. And the takeaway here is there's these four, which represent 96% of your body. Most of you is oxygen, followed by carbon, hydrogen, and nitrogen. Pretty much these four elements make up 96.2% of your body. Oxygen, carbon, hydrogen. Why? Well, it's because much of us is made up of water, which is why there's so much oxygen and hydrogen in us. But then the rest of it, the carbon and the nitrogen and some oxygen and hydrogen, makes up these four different categories of biomolecules. All right, proteins, carbohydrates, lipids, and then nucleic acid. I didn't talk about nucleic acids much, but this is DNA and RNA, the genetic stuff. There's much less of this than the other three. So these categories, carbohydrates, lipids, proteins, and nucleic acids, are polymers. They're called biopolymer, meaning we make a big chain. It's like Legos. We're going to take, you can have an individual Lego block, and you can put them all together to make the Millennium Falcon. So like this is the Millennium Falcon, and these are the Lego. No, the other way around. This is the Millennium Falcon, these are the Legos. So in this category of carbohydrates, lipids, proteins, nucleic acids, the monomer of a carbohydrate is called a monosaccharide. I'm going to show you a slide in a moment. Also called simple sugars. Simple sugars. And those simple sugars make polysaccharides or complex carbohydrate. Lipids, the monomers are fatty acids and glycerol, and they can make up fats. I use the word triglyceride, and we'll see that in a moment. Proteins, the monomer is an amino acid. It makes up polypeptides. As those get longer, we call those proteins. And then the nucleotides are what we make DNA and RNA.
So when you
an example would be something like an amino acid is a monomer of what category of biomolecule? Protein. Or I might ask a question like, give me an example of a polymeric lipid. The triglyceride. We'll see that it's a type of. Or directly from this slide, it may be something. Describe for me what a polysaccharide is. Well, it's a polymer of the carbohydrate above. Does that make sense? All right. So then this slide, I amended it a little bit because you guys wanted some writing on the slide, so I did that. And I say here, dietary sources of amino acids are used to make proteins. Proteins can catalyze reactions and build structures in cells, etc. We put ETC. There's a lot. Yeah, amino acids polymerize to form proteins. So here is the fundamental, like a schematic of a general amino acid. The backbone, there's 3 atoms in the backbone: the nitrogen, an alpha carbon, and the organic acid. So that there's the acid end, the amino end, which makes them an amino acid. And in the middle, there's this alpha carbon, which has an R group attached to it. There are 20 different R groups that are responsible for all the different types of amino acids, which are what give us the different types of proteins. So this is a ribbon diagram of what a protein, a structural protein, might look like, or maybe it's a catalytic protein. Yeah.
Which thing? What? So amino acids.
Yeah, amino acids
Is
are
like number
amino acids make up monomers make up polymers within a certain category. Does that make sense?
Yeah. So.
Yeah, this is like a, I don't know, I didn't make this chart.
So
but
when you say that it's
polymerize.
polymerize.
Yeah, proteins, shorter amino acids are called polypeptides. They're called polypeptides because the bond that links amino acids. This chart was presuming that I was going to give the whole lecture about amino acids and proteins, which it became clear that. But the bond between amino acids is called a peptide bond. And if you start linking amino acids by multiple peptide bonds, it's a polypeptide. And then eventually, after like 30 or 40 amino acids, we begin to. That's right. Yeah, this is a category. This is the category. This is what we would call a polymer within that category, and this is a monomer. And like this is kind of a reductive schematic in that the nomenclature across the 4 categories is not quite the same. That relationship and the nomenclature is not quite the same because they're like totally different types of molecules, right? Like a fat is completely different than a nucleic acid. But it's like a kind of a simplistic way to understand them. That's right, yeah. Okay, so then sugars, aka carbohydrates. The monomer is called a simple sugar or a monosaccharide. Mono meaning one, simple sugar. You get your carbohydrates, dietary carbohydrates get broken down by your body into simple sugars and absorbed. So some examples are glucose and glucosamine. Those sugars get used to do all kinds of different things, built up to form these complex carbohydrates. So for example, glycogen is a polymer. It's a polysaccharide of the monosaccharide glucose. This glycogen is important because it's stored in your liver and muscle cells and is the way that you store energy, carbohydrate. It's how you stabilize your blood sugar. It's as glycogen. Glucosamine, for example, is used to make cartilage. So the thing I wrote here, dietary carbohydrates are used to make complex carbohydrates, which have many functions, many functions. A question from this might be something like, maybe give an example that was discussed in class of a type of polysaccharide. Could could say glycogen. Or give an example of a monosaccharide or simple disgusting. Glucose. Glucose. Fatty acids. So fatty acids are the fundamental unit of a fat, right? And it has this long, greasy tail, and then an acid chain on the end. So there's like a fat and an acid. So a long, fatty, greasy tail, and this acid group. It combines with glycerol. It polymerizes to the bigger structure here is called a triglyceride. Yeah, and triglycerides are the way that we store energy, fat energy. That's how your body stores. Pretty straightforward. Yeah, a fatty acid is made up of a greasy tail and an acid group, an organic acid. 3 of these things combine with a molecule called glycerol, which is this baby, to form a triglyceride. This is a glyceride bond. It forms what's called a glyceride bond. And these 3 fatty acids all park on a little portal here on the glycerol backbone and form a triglyceride. Triglycerides are how your body stores fat. That's the method by which it's the molecule that fats are stored as in the body.
So like a fatty acid.
What are the constituent parts of a triglyceride? Or how are fats stored in the body as triglycerides? Or describe the parts of a fatty acid, detail and acid.
So, call the triglyceride even there's.
Yeah, there's 3 glyceride bonds.
Oh.
A triglyceride, yeah.
Okay, so it's just one.
3 glyceride bonds. Make sense?
Yeah.
And I added one more slide of triglycerides because fats do much more than just store energy, right? They life would not be possible without them. And in fact, cellular life probably was not possible until the advent of fats because what happens is these triglycerides are not very polar. They don't really like to be in solution. And so we have to make them what's called amphipathic, or having a part that's greasy and a part that's polar. And we do that by taking one of these fatty acids, ripping it off, and replacing it with a phosphate group. And we make these phosphoglycerides. It's making a phosphoglyceride bond. Phosphoglyceride. Phosphate is very polar. It's very polar. And so then these phosphoglycerides, if we look here, here's carbon 1, 2, and 3 of the glycerol backbone. Here's fatty acid 1, here's fatty acid 2, and the third one's gone, and it's replaced by this phosphate group. All right. Now we have a very polar end and a very nonpolar fatty acid tail, and they all line up in a row with the polar heads facing the water and the greasy tails in towards the inside of a lipid bilayer. Here's one leaf of the lipid bilayer, and here's the other. All right, phosphoglycerides. It's what makes cells possible. It's what makes cells. Yeah. Yep. Yeah, you take one of the fatty acids off, and you replace it with a phosphate. Form phosphoglycerides by replacing one fatty acid with a phosphate via a phosphoglyceride, and then take home being that phosphoglycerides are important because we wouldn't have cells. There would be no story to tell. Yeah. Scribble. I go on. We're getting pretty close to the end here. So then I basically bailed on all of the stuff in between here, the biomolecules and the cell, like cell structure, and I jumped right into the organ system. So again, this is the level, the hierarchy of life: atoms to biomolecule to molecules, biomolecules, cells. It's kind of skipping tissues to the organ level to the organ system. And eventually, I went through each of the organ systems. I talked about the integument, or the skin. I talked about the skeleton, the muscular system, the nervous system, the endocrine system, the cardiovascular system, the lymphatic system, the respiratory system, the digestive system, and the urinary system. I didn't talk about probably. Yeah, and so in terms of the organ systems, I would say that the things that I talked about in class, and I can go through them again briefly, but I talked for each of the organ systems. I talked about what the major organs were and what was like the general function. So I would expect you to know what the organ systems were. So, for example, the cardiovascular system is made up of the heart, the arteries and veins, and the blood. Parts of it, yeah.
Is this those questions?
I haven't made the test yet, so I don't. But depending on the time that I have, if I have the time to make a multiple choice test, I will. I'd like to. The chances of me having it, because those are super time to make, me having one that covers all of this material is unlikely. So what's probably going to happen is probably going to be in multiple choice questions like that. I'll do a short form that will apply to the questions that are amenable to, and then there'll be some other ones. Well, I'm not asking you specifically to name them all, but I would like you. I mean, it would be smart to be able. I'm not going to ask you to name them all, but I think it would be smart to be able to do that, right? I'm not going to. That seems like a silly thing. Name all the. Yeah, yeah. I went through. I took 2 classes and went through each of the organ systems and what a part of that organ system was. So an example. Yeah. And so, for example, and I can pull those slides up again if you want to look at them, but in the respiratory system, I said that the main parts of it were the nasal passages, the pharynx, the larynx, the trachea, the bronchi, and the lungs and the alveoli. the parts. Huh? Yeah, that nasal cavity. And the primary function of the respiratory system is gas exchange, so releasing carbon dioxide, absorbing oxygen. I also said that it had a role in regulating the pH of the blood. I believe I did. And it also has a role in phonation, a generation of sound. That's right. Would you guys like me to pull up those slides?
So I didn't.
Digestive and urinary? Yeah. Would you like me to? All right. So anyways, this was the last thing. Super mega fun time human feedback experience on Tuesday. Let's see, where is it? It's not. Organ systems. So digestive system. Yeah. The digestive system is, the stuff that's in your mouth, your teeth, your tongue, etc., which then leads into what's called the pharynx. It's the back of your throat, the common tube through which both air and food pass. And then eventually the food separates from the air and goes down the esophagus. The epiglottis closes over the laryngeal apparatus and allows the food to pass by when you swallow, and it goes down into the stomach, and then begins, after it's done being digested in the stomach, it passes to the small intestine, the colon. And then I said there were 3 accessory organs. The liver and gallbladder, which are hair. The third is the pancreas. And the liver, the gallbladder, and the pancreas all secrete digestive enzymes and dump them into the small intestine. So, the function of the digestive system is intuitive to you guys, particularly at this day for lunch. The processing and digestion of food. So processing means chewing, mastication, food, and then digesting, breaking the starch, food that you down, that your body can absorb. And it's not just food, it's also water. The digestive system is responsible for absorbing water. And when I say conserving water, when it says conserving water, so your body actually puts more water into the food that you absorb than you drink, typically. So we'll see that in the digestive chapter. But it has to take it back out again before it passes. And if it doesn't, what do we call that? Diarrhea. And diarrhea will kill. So you need to, from dehydration, you need to be able to absorb and conserve the water in the body. And so, the absorption of nutrients, ions, nutrients, sugars, the fats, the proteins, the electrolytes. So that's all that's like straightforward functions of the digestive system. However, There's one other that's a little bit less appreciated, and that is the storage of energy. And that specifically happens in the liver. The liver stores glycogen. I showed you glycogen, which is a polymer of glucose. Animal starch, vegetable starch is what we call amylose. It's the scientific. Eating a raw potato, flavor, starch. You bake it, you break the sugars. But in humans and animals, that starch, we use starch as well, but we call it amylose. And it lives, you don't need to know amylose, or I'm sorry, glycogen. You do need to know glycogen. It lives in the liver. So that's the storage of energy reserves. Well, this was the organ systems set of slides. So I think there should be 3 slide posts. There was the first one that was like a bunch of slides, and I only got through the first couple of those slideshows, and I skipped the 3rd and the 4th or whatever. And then organ systems, I think, is labeled 4. And then I think homeostasis is labeled 5, and I didn't get to homeostasis. Yeah. All right. And so then, lastly was the urinary system. And the urinary system is actually pretty straightforward in terms of the organs. It's just the kidneys, which produce the urine, the ureters, which transport the urine from the kidneys to the urinary bladder, which stores the urine, and then the urethra, which is the pee hole that. Okay. And the job of the urinary system. It has more jobs than you may imagine. So it isn't just the production of urine. That urine itself, but okay, first of all, it is the production of urine. And the production of urine is the process by which the body eliminates fluid waste. Solid waste passes through the GI tract, digestive, and fluid waste is eliminated from the blood via the urinary. A corollary to that is that it's going to control water balance by regulating the amount of urine produced. So, for example, when you wake up in the morning and you urinate, is that the same color as the urine that you may have in the day? It'll be darker because your body's trying to conserve water as you sleep. You're not. So if the urine is produced all day, you have fluids, and the urine is more dilute. So urine can get stored. If you were people who are old people, men who had prostate surgery, babies have lost bladder, who are not able to control the urine. Diapers often catheterized because the kidneys are producing. Everyone else is fortunate for bladder, store it up, leaking. Yeah. Do those Kegel exercises. So it also regulates the pH and the ion concentration in the blood. And I would go further than what this slide says. It also is important in regulating blood probably imagine that because your blood pressure is related to how much fluid is in your body, and remove fluid from your body. So it's more complicated. The kidneys have a role in regulating. Yeah. Well, it's under more stress. Yes, it's under more stress. But if you are a person who doesn't drink a huge amount of water, or it has their diet under control, where you're not prone to high blood pressure, because high blood pressure will destroy you. High blood pressure. You get high blood pressure by having a bad diet. And but if you're not prone to that, if you're like a healthy individual, you can live a long, happy life. Those people need to be concerned about making sure that they take care of their kidneys, because they have half the capacity. The one perfectly capable. Yes.
So it's just like
I don't know. That's a very good question, and I could speculate, but I cannot give you a. I think that's that is not. I don't actually. That's a developmental question. It's a developmental that I would have to ask a comparative biologist. Look it up. Well, yeah. I don't know.
Maybe it's just well, it's not really.
One liver. Yeah, we are biradially lung, heart. Yeah. The thing with the kidneys, I guess it is an speculation. It's an evolutionary advantage. The thing to the kidney is if like one kidney can do the job of two, but no kidneys, you die quickly. So if you only have one kidney and one of them, did you look it up, Tim? Okay. That's the question we're answering. I'm answering. Wow. Yeah. So the if you have two kidneys and one of them is screwed up, then you have backup, and your kidneys are actually kind of vulnerable. They're right here.
I know.
And so, like, if you touch, if you push along your back, you can feel the bottom edge of your rib cage back there. Like I feel my bottom edge right here. Your kidneys are just below it, and if you get hit back there, it can be kind of painful. And if you get hit hard, you can have blood in your. It's pretty easy, and they're close to the surface. There's no bone protecting them. They're totally at the back. They are so far back, it's what's called retroperitoneal. The only thing protecting the kidneys are those sort of two bands of muscles that you feel that run on either side of your. You know what I'm saying?
See, yeah. Rather than just like straight on.
So here is a person from the side, and the kidneys are like right there.
Oh, right.
Adrenal gland. Yeah, the suprarenal gland. Yep. Yeah. Yeah. Well, I mean, it's in like a totally different. Your esophagus. Your esophagus only goes down to here to the stomach, right? So they can only get right around here, and this is way down.
It was a question.
Mars.
Can we look at obviously off systems?
Posterior. They're in the posterior wall of the abdominal, in the back wall of by the layer. All right, and you had a question. Yep. Nope. Yep. They go through your back.
That's what I thought. The back.
It's an incision right. It's an incision right here.
Don't eat this.
Yeah, they lay you on your stomach. Any other questions? You want me to go through any of these other systems? I'll go through them quickly. You've got 5 minutes here. A question about the integumentary system. You did. Skin.
Skin. Oh, skin.
I don't remember.
I don't. Yeah.
Huh? That's right. Yeah. Do you have a question about it?
No.
Skeletal system. Bones, cartilages, ligaments, marrow. Support, protection, calcium storage, blood cell formation.
They store.
It stores it. Yeah, I mean, that's what it's using it, but it can take it. That's the body's innate storage of calcium. You don't keep calcium. It's being used, but the vast majority of the calcium in your body is in your skeleton.
Oh, okay. Because I read somewhere.
That is, but that does not sound. Yeah.
I've also heard excessive. Why?
It depends on your individual physiology, but in general, if you are not lactose intolerant and have no other sensitivities to milk, milk is a fine source of calcium and protein.
So I could just drink a lot of it.
Seems like you would be fine.
There's
As
a
long
lot
as
of
that's right.
Yeah, look, I mean, milk is one of those things. Milk was designed to feed infants, right? And then at some point, about 10,000 years ago, in Germany, a mutation arose in the human gene pool where children that were older than 3 years old, the enzyme, the lactase enzyme that infants make that breaks down the lactose in milk sugar, your body stops making it after 3 years of age. But 10,000 years ago, in Germany, a mutation happened where a person was born, I don't know who, 10,000 years ago, was born who didn't stop making it into their adulthood. And they were able to drink both mother's milk, I guess, if that was happening, or the milk of other mammals into adulthood. And that was an evolutionary advantage because suddenly they were able to drink the milk of cows. Prior to that, there was no drinking milk of cows. And then there was the Norman invasion that spread into England, and that brought this gene all throughout Europe. So most people of European descent are mutants. We are able to produce lactase that enables us to consume milk and digest the lactose that's in it.
So
There was another mutation that happened in Africa, so a lot of people of African descent, the same, but people of Asian descent often are lactose intolerant. That is not a problem with them. That is how humans all used to be.
you
No, because they're spontaneous lactose intolerant.